Welcome to MRS Bulletin's Materials News Podcast, providing breakthrough news and interviews with researchers on the hot topics in materials research. My name is Sophia Chen. Kaveh Ahadi, a materials physicist at The Ohio State University, studies an unusual material. It's a film of lanthanum manganite grown on a crystal of potassium tantalate. It turns out, when lowered to the temperature of 2 Kelvin, this material is a superconductor, which means it conducts electricity without resistance. But Ahadi's recent work found something even more unusual. This material remains superconducting even in a powerful magnetic field. Usually, magnetic fields tend to destroy the superconducting state in materials.
We believe this is an interesting case that does not fit other explanations of a superconductor that is highly robust against magnetic fields.
Ultimately, scientists want to study these materials to improve the sustainability of our electric infrastructure. Superconducting materials don't lose any energy as waste heat, so theoretically, electronics made of superconductors would be extremely energy efficient.
One avenue why we like superconductors that are robust against magnetic field is that then we could build, in general, magnets with superconductors which are less energy consuming.
For example, researchers are looking to create increasingly powerful magnets for applications such as particle colliders. They could make these magnets by taking a superconductor that is robust to magnetic fields and making a giant coil of it. But researchers aren't close to those applications yet. And to be clear, Ahadi's material isn't practical to use. But Ahadi says that studying this material will help researchers better understand the mechanisms that lead to superconductivity. His team aimed to figure out how the material managed to stay superconducting even when they applied extremely strong magnets to it at the National High Magnetic Field Laboratory in Florida. The material experienced 25 Teslas of magnetic field and stayed superconducting. That's about 10 times stronger than the magnetic field used in MRI machines.
And it was exciting. To be honest, it means that we don't see anything. We see resistance remains not detectable. But that was a sign that it's highly robust against magnetic field.
The superconducting state resides at the two-dimensional interface between the crystal of potassium tantalate and the lanthanum manganite film. Potassium tantalate is a transparent cubic crystal. In 2021, scientists at Argonne National Laboratory in Illinois found that layering potassium tantalate in a particular orientation with other materials will create a superconducting interface. However, that particular surface of the crystal is highly electrically polar and rough.
So it was a material science challenge to grow highly perfect interfaces.
Ahadi's team worked with theorists to come up with an explanation for why the material can maintain superconductivity in the magnetic field. To understand why, let's first talk about how superconductors conduct electricity differently from regular conductors. In a regular conductor, electricity flows through the motion of single electrons. In a superconductor, on the other hand, electricity flows through the motion of paired electrons known as Cooper pairs. In Ahadi's material, the electrons' quantum spins are strongly influenced by their motion through the material. This is known as spin-orbit coupling. The spin-orbit coupling changes the electron's magnetic properties.
Because of a spin-orbit coupling, we could have electrons that have a very small effective magnetic moment. And because of that, our Cooper pairs might not couple to the external applied magnetic field as strongly.
In future work, they will study this material further with the goal of elucidating the principles for designing practical superconductors that are robust to strong magnetic fields.
We are still planning to make devices out of these, like Josephson junctions, to understand more or study more fundamentally to understand the superconductivity here.
They will also study properties of other orientations of the potassium tantalate crystal. This work was published in a recent issue of Nano Letters. My name is Sophia Chen from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org and follow us on X @MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.